Hello, everyone. Welcome to MACSMIN 2025. Now, Dr. Gemma Flor will talk about comparison of isopointal crystal structures using COMPSTRU. Gemma, please, over to you.
Thank you very much. Good morning, everybody. It's a real pleasure to be part of this seminar again. I have the chance to join the MACSMIN 2022 in Liverpool, and I'm very happy to be back with you today, even if this time is in an online format. So I'm excited to share my talk with you entitled Comparison of Isopointal Structures using the Bilbao crystallography, using the program COMPSTRU that is available in the Bilbao crystallographic server. Okay, now why it's not? Okay, now. So here is an overview of the content of my talk. I will begin by reviewing some key points, in particular the concept isopointal and isoconfigurational structures. Next, we will look at the comparison of structures, why it's necessary and how it can be approached. I will then introduce the method for the comparison on which our program COMPSTRU developed within the Bilbao crystallographic server is based. I will not only explain the method, but also present some illustrative examples. And finally, I will discuss the limitation of this approach, and I will be very happy if this leads to further discussion within the audience. So I'm not sure if all of you are familiarized with the term isopointal. Therefore, I have prepared this slide. So two structures are defined as isopointal if they have the same space group type or belong to a pair of enantiomorphic space groups, and the atoms are occupying the same sequence of Bykov positions. So here as an example, we have the structures of sodium chloride and magnesium oxide. As you can see, these two structures belong to the same space group type. They belong to the space group number 225. There are two atoms in the asymmetric unit in both the structures, and the atoms in both the structures are occupying the same sequence of Bykov positions. So this means that these two structures are isopointal. Now let's have a look to another example. Here we have two enantiomorphic structure descriptions of aluminum phosphate, one described in the space group 152 and the other one in the space group 154. In this example, the structures are also isopointal. Their space group form an enantiomorphic pair, and the atoms occupy the same sequence of Bykov positions. Now that we know what isopointal means, let's move to the next concept, that is isoconfigurational. So two structures are defined as isoconfigurational or as belonging to the same structure type if they are isopointal, and for all corresponding Bykov positions, both the crystallographic configurations and the geometric interrelationship are similar. The notion of similar is not strictly defined in this definition, which makes this second condition difficult to quantify. I mean, if you are curious about these definitions, you can find them here in this paper here. So according to this definition, sodium chloride and magnesium oxide can be regarded as isoconfigurational structures, or equivalently, as belonging to the same structure type. Now let's move to another example.
Gemma, could you clarify the concept of isopointal? If you take a very simple example of, say, rectangular lattice, two-dimensional, if you make the rectangular cell, say, a bit longer, without changing anything else, so simply stretching in one direction, then we will have the same isopointal configuration or lattice in this case, right? So stretching the rectangular unit cell. I see. And in that particular case, you call them isoconfigurational. So this is a strong relation because the edge lengths of a cubic cell here are similar.
Yes.
So
I mean,
with
here,
values.
here you know that at the end you have to have a look to this geometric interrelationship. So at the end, this is a very easy case because you know the atoms are exactly occupying the same position. Let's have a look to the next example because they are not configurational. Here you have a pyrite and a carbon dioxide, a solid carbon dioxide. So the structures are isopointal. They are described in the same space group type. We have the same number of atoms in the asymmetric unit, and the atoms are occupying the same sequence of Bikov positions. You know here the sulfur atom is occupying the Bikov position 4C, that is XXX, with X equal to 0.348, and here the oxygen atom is also occupying the position 4C. XXA, but here X is 0.118. Here, according to this definition, but as I said, this definition is a little bit vague because you don't know here, pyrite and solid carbon dioxide are not considered isoconfigurational. They are not considered that they belong to the same structure type, since this parameter deviates too much. That's what is said in the literature. I cannot hear you, Vitaly.
Yes, Gemma. So this is an example of isopointal, but not isoconfigurational structures. Okay,
Yes.
and the reason is that these two values of X are too different.
Yes, that means it's not that they are different, it's that they don't belong to the same structure type, so that they will belong at the end. This classification of structures and the structure types is that you take a family of structures and you try to classify them like in subfamilies, because then maybe they have similar properties and so on. I mean, I would say that the structures are similar, but in this case, they do not belong to the same structure type. It's a different concept. I mean, the concept is a configurational. I introduced because the program COMPSTRU only is able to compare structures that are isopointal. And then I introduced the concept of isoconfigurational that we will see later on for this application of the classification of the structures into structure types, and also to see that this is still an open problem because the definition is quite vague with this.
May I say something?
Yes.
In your showing of CO2 in the solids, you don't show the dumbbell. I mean, I don't see the molecule here. You add some bonds with which criteria you connect them to the other. So this is a little bit delicate also to see, because one thing in this approach, there are no bonds, there are point sets. So you're comparing point sets in some way. But here you draw some bonds with which criteria. I don't see where is the carbon, where is the oxygen, where are they exactly. So it's a bit... I agree that they are not isoconfigurational, but this has to be careful. I mean, this is not a really good example, because CO2 is a molecular crystal or is an infinite crystal. Because if it's a molecular crystal, you have to show CO2, and then there are non-bonding interaction between each CO2. Instead, here you show something that everything is connected to everything. So it's not a good example to show this. I mean, it's good from the point of view that these two are isopointal, but they are not isoconfigurational, because it's self-evident, let's say, looking at the structure. So it's
Okay, thank you. So I will, for the future, I will have a look to this. I will not show these figures here. I choose this example because it's one of the examples that is in the literature.
It's not the best choice in my point of view.
Then I will take it in account.
One, if you compare the topology, then it's another story. But in this way, but anyway, it's from the point set reason. Yes, they are not, because the X is very different from the other, and so. So the passage to isoconfigurational from isopointal depends on some matrix. So it's anyway, you can go ahead. So
at the end, this the method that I'm going to introduce today, we are not having into account, as we will see, we are not focusing on the chemistry. We are just only focusing from the structural point of view. Okay, so I take a note. Thank you very much, and I will try to find for the next time another better.
The structural point of view as a point set. So
yes,
you don't consider bond. You don't
yes.
care about the bonds. So
Exactly.
that's the approach is very from physics. Let's say people from physics, they think in this way. People from chemistry thinks also with the bonds. But that's
okay.
Okay.
Thank you for your comment.
Thanks.
Okay, so now that we have these two concepts of isopointal, I mean, they will come back later on, that we have these two concepts kind of clear, let's continue with the comparison of structures. So a qualitative comparison of similar crystal structures is often convenient to cross-check different experimental or theoretical structural models of the same phase coming from different sources. So it is also important for the identification of different phases with the same symmetry. And it's fundamental for the still open problem of the classification of structures into structure types. So in most cases, even if the setting of the space groups is fixed, there is more than one equivalent description for a given structure. So the existence of various equivalent structure descriptions makes a comparison of different structural models a non-trivial task in general. So let's have in general, structures, as you know, are described through the space group symmetry, and unit cell parameter, and the atomic positions in the asymmetric unit. This description depends on the coordinate system, in other words, on the chosen setting of the space group. However, even after fixing the setting of the space group, in most cases there are several equivalent but different descriptions of the same structure. So there are almost always several possible ways to describe the same crystal structure. For example, for the structure of cesium chloride that is described in the space group PM3'M, the origin can be chosen at the center of the cesium or of the calcium atom, which result to these two different sets of coordinates. In this case, the equivalence of those description is easy to recognize. So we can go from one structure to the other one just by a simple translation of the type 1/2, 1/2, 1/2. However, in many other cases, this is not simple to recognize whether two differently documented structures are alike or not. So here the question that arises is how many equivalent descriptions of the structure of cesium chloride exist? Or in general, for another structure, how many can we quantify? Can we know how many equivalent description a structure can have? So the answer is yes. So there is a way. So for all space groups, except for these two cubic one, several different sets of atomic coordinates can be chosen to describe the same structure within the same space group setting. The number of such equivalent coordinate sets for a space group G is exactly equal to the index of the group G in its Euclidean normalized. And then if you calculate the causa decomposition of the Euclidean normalizer with respect of G with respect to the space group G, the causal representative arising from this causal decomposition will generate the different equivalent descriptions of a given structure. So the calculation of these equivalent descriptions is essential for comparing structures. In general, the comparison of two supposedly similar structural models requires considering the possible existence of multiple equivalent descriptions. This means that the process cannot be reduced to a direct comparison of unit cells and atomic positions. Instead, for one of the structures, all the alternative equivalent descriptions compatible with the space group setting must be explored. So let's go back to the example of sodium chloride. So using one of the programs available in the Bilbao crystallographic server, the program normalized, we can determine the Euclidean normalizer of the space group of this structure. So the Euclidean normalizer of the space group PM 3 bar M is shown here, and the index in this case is equal to 2. This means that there are 2 possible sets of coordinates. The additional symmetrical equivalent descriptions are obtained from the original one, applying the additional generators of the Euclidean normalizer. In this case, the additional generator is a translation of the type 1/2, 1/2, 1/2. So here at the end, so as we there are only these 2. In this case, there are only 2 descriptions, 2 symmetrical equivalent description of the structure of cesium chloride, and one can transform one from the other one, applying this translation of the type 1/2, 1/2, 1/2. In this case, the equivalence of both descriptions is easy to recognize. However, in many other cases, it is not so easy to recognize if 2 structures are similar or not. In this case, it's straightforward to answer the following questions. Are the 2 structures of sodium chloride similar? And in this case, is yes. It's not that they are similar, it's that they are identical. So they are symmetrically equivalent. But the answer of this question is not always so easy. So let's have a look to the following structures. Here you have the data for each of the structures, and here you have, I have drawn them in Vesta. In this case, only with this data, it is not easy to answer the question, are these 2 structures similar, or are these 2 structures 2 different phases of the same compound? Yes, by looking at the structure, at least I am not able to answer these questions. So that's why, based on the normalized space groups, we develop a program called COMPSTRU in the Bilbao crystallographic server. And now in the next slide, I'm going to briefly introduce the algorithm, the method in which this the algorithm in which this program is based. So as input, we have 2 structures. The first one is always kept as the reference, and the program first calculates all the symmetrical equivalent descriptions of the structure 2, and try to find among those the one that best matches the reference structure. So each of these equivalent description is specified by a coordinate transformation described by a matrix column pair that is obtained by combining elements of the affine and the Euclidean normalizer. From the elements of the affine normalizer, the program finds the best match of the lattice parameters, whereas the elements of the Euclidean normalizer find the best match of the atomic coordinates of the 2 structures. So the description of the second structure, more similar to the referent one, is called the most similar configuration to the description of the structure 1. This most similar configuration is chosen among the symmetrical equivalent description of the second description, so that the strain is minimum and the maximum difference of the atomic positions of the matching atoms has a minimum value. Now, in a second step of the procedure, the similarity between the reference and the most similar description of the second structure is quantified. But how do we measure the similarity between these 2 structure descriptions? So we calculate some parameters that I'm going to show you now in the next slides. So the program COMPSTRU evaluates the similarity between the structure by calculating different measures. So by different measures. The similarity between the lattice parameters of the structures is measured by the degree of the lattice distortion. Then the difference between the atomic positions of the matching atoms is also calculated. And this is measured by the maximum difference between the atomic positions of the matching atoms and by calculating the arithmetic mean of the differences between the positions of the matching atoms. And also, the program calculates this measure of similarity that is based on the formula of Berger's law. So here you have it. As you can see, it's a function of the differences in the atomic positions and the ratios of the corresponding lattice parameters of the structures. The measure of similarity is calculated as an additional descriptor, and one have to have in mind that the program does not standardize the structure description to calculate this value, as is done in Bergerdorf et al., and may therefore differ in some cases from the values of Bergerdorf, but those values, the differences are very small. Now that you have an overview of the method in which that we use to evaluate the similarity between two isopointal structures, let's have a look to the program and let's apply it in some real cases. So for those who might not be familiarized with it, the program COMPSTRU is available in the Bilbao crystallographic server. That is a free online platform that provides access to crystallographic databases and more than 100 computational tools for solving problems in crystallography, mineralogy, chemistry, physics, and material science. So the server is fully web-based. You don't need to pay, download, or install anything. Simply type in the address into your browser, and you can start using all the available programs. As you can see, the server is organized in different sections, and the programs for comparing crystal structures. So the program COMPSTRU is located in the section dedicated to structure utilities. By clicking, so when you click in this section, here you have all the programs related with structures that we have available. And here you can find the program COMPSTRU. So by clicking on COMPSTRU, you are directed to the program's input page. So the program is very easy to use. As input data, you need to provide the two structures described with respect to the standard setting. These are a specific setting of a space group that coincides with the conventional space group description found in Volume A of International Tables for Crystallography. For a space group with more than one description in the tables, the following settings are chosen as a standard. So unique axis B, cell choice 1 for a space group within the monoclinic system, hexagonal axis for hombohedral space groups, origin choice 2 for centrosymmetric space group with orthorhombic, tetragonal, and cubic systems. So if your structures are not described in a standard setting, you can also, we have some also tools in the server that can help you to transform your structures from a non-standard setting to a standard one, such as tools, for example, AccessTru, TransTru, or SIF to a standard. So you can upload the C files of the structure in the program directly, or you can introduce the description of the structure in this text box in which in what we call the VCF format. The information that you need to provide in this text box is the following, and in this specific order. You need to provide the space group number, the lattice parameter, the number of independent atoms in the asymmetric unit, and then the atom type, number, Bykov position, and XYZ coordinates. So at the end of the input page, there is a section dedicated to the tolerances. By default, the program assigns values for the maximum difference in the position of the matching atoms and on the lattice parameters. So it is recommended that not to modify these values, since if you need to increase them, the program will complain and ask you to increase the values of either one or the other one. And then the user also have to have in mind that if then when increasing this value, if it makes sense for it for the result that is getting or not. Then remember that the program COMPSTRU is able to compare structures, isopointal structures, with the same or different composition, and also to compare chiral structure descriptions. So let's go back to this example, and let's analyze if they are similar structures or they are two different phases of the same compound. So if we introduce the structures in the program COMPSTRU and we click on show, we will arrive to this intermediate form. So here the program provides a list of transformations that best matches the lattice parameters of the structures for the chosen tolerance. So the element of the affine normalizer that best matches the lattice parameters of the two structures is usually highlighted in red. In these cases, there is only one choice, so that's why I'm explaining this, but there is only this choice. So then you select it and you click on continue, and then the program performs the calculations, and here is shown the part of the output, a summary of the output of the program COMPSTRU. So here, first, the input structures descriptions are shown, the description of structure 1 and structure 2. Below the description of structure 2 is shown the description of structure 2 in a more similar configuration to the description of structure 1, together with the transformation metrics. So if we apply this transformation metrics to structure 2, we get the description of structure 2 in a more similar configuration to structure 1. Have in mind that this is one of the symmetrical equivalent descriptions of structure 2. Then also the program shows information related to the matching atoms and the differences in the atomic position. At the end of the page, we get the most important information, that is the evaluation of the similarity. So here you have the degree of the lattice distortion, the maximum distance, the average distance, and the measure of similarity. That this is what the program calculates. The program does not give you a yes or a no to the question, are these structures similar? It's the user work to evaluate these numbers and answer the question. As I said at the beginning, this is just a pure structural analysis. The program does not have the chemistry into account, or doesn't have any kind of chemistry analysis. So it's then the user who has to have a look to these values, and depending on the case, to evaluate if the structures are similar or not. Because sometimes two structures are going to the value that means that two structures are similar for one case may have another meaning for another pair of two completely different structures. So in order to help the user to interpret the results, the program provides another option to evaluate the similarity. So we have an option to visualize structures. So if you click, for example, here, or here structure 1 and structure 2, you can visualize separately your input structures. Here you have, if you click here, you will visualize the most similar configuration of the structure number 2 with respect to the reference structure. And for example, if you click here in compare structure, the program will visualize together the reference structure with a more similar structure. And here, for example, if you click on compare lattices, the program is going to simultaneously plot together your two input structures. So here we are giving also another visualization to another tool to the users to try to interpret the results. So considering the values that measure the similarity and the visualization of the the results that we obtain from visualizing the structure, I think that I have convinced you that these two initial structures that were very different are similar structures, that they are not two different phases of the same compound. The program COMPSTRU is also able to compare isopointal structures that have different compositions. So let's have a look to these two structures, and let's determine with the program COMPSTRU if they are equivalent or not. So if you introduce the structures in the program and you click on show, you will get this, you will be redirected to this intermediate page where the program first calculates the best match for the lattice parameters of the structures. So here all the equivalent unit cell parameters are calculated and compared with the unit cell parameters of the reference structures. Here, in this case, we have two possible solutions, and the one with less strain, I mean, practical, is this one, so that's why it's highlighted in gray. And when you click into continue, in this case, as the structures have different compositions, the program is going to redirect you to another intermediate form, in which here in this page, the program is going to show you the corresponding scheme between the atom species that is going to follow to evaluate the similarity. So if you agree with this correspondence proposed by COMPSTRU, you click on yes, and the program will carry out the calculations. And if you want to try another correspondence between atomic species, you can always click on no, and you can indicate the program your own correspondence. So this is a very nice option, but I would suggest that only to use it to people who knows really what they are doing. So I mean, if you are a beginner in comparing structures, I would suggest you to follow the proposed correspondence scheme that is given by the program COMPSTRU. Because if you try to do this by yourself by hand, and you are not, you might try to do something that can give you a completely incorrect comparison. So this is the last step that you have to make before the program make all these calculations and evaluate the similarity between the two structures. So here you can see the summary of the results of the program, and checking the values of the different quantities, and also if you plot together, use the visualization option of the program COMPSTRU, you can say that these two structures are quite similar. Now let's have a look to a last example, because as I said before, COMPSTRU can be used for a comparison of chiral structures whose symmetry space groups form an enantiomorphic pair. So in this example, a pair of chiral structures of aluminum phosphate in a space group number 152 and 154 are compared. So if you introduce these two structures in the program and you follow the different steps of the program, you should arrive to an output page like this one. So one should have into account that in order to compare the structures, the program COMPSTRU have to transform the second structure into its enantiomorph through the inversion. And this enantiomorph is compared with the reference structure following the usual procedure. Here you have the transformation metrics, and you can see that the determinant of the transformation matrix is negative as expected, switching the chirality from one structure to the other one. So the similarity of these two chiral structures is quantified by the calculated by these parameters, whose values indicate that the structure can be considered as nearly enantiomorphic. So the program COMPSTRU can also be used for more complicated problems, and we are coming back here, such as the classification of isopointal structures into isoconfigurational structure types. A systematic comparison of isopointal structures with different compositions is required for the classification of structures into isoconfigurational structure types in order to recognize different compounds with identical or nearly identical atom arrangement, facilitating the prediction and understanding of the crystal properties. The classification of crystal structures into structure types has been, as I said before, a difficult problem in crystallography since its beginning, and is still an open problem. The different definitions and procedures for the classifications and measures of similarity have been suggested and tested over the years. You already know two structures are defined as isoconfigurational or that they belong to the same structure type if the structures are isopointal, and for all corresponding Bikov positions, both the crystallographic configurations and the geometric interrelationships are similar. And again, this term similar is specified for this condition, and that's why it's so difficult to quantify and implement in algorithms for automated computer searches. So in fact, the program COMPSTRU can be applied in these types of problems. Here we have an example. Here I'm showing a study that we did on this family. Here are shown some of the structures that belong to this family. And the question here was, can we distribute these structures into isoconfigurational structure types? And how many isoconfigurational structure types are? We have done this study using the program COMPSTRU. We can take as the reference structure calcium hexafluorochromate, and then applying the criteria of the maximum difference of the atomic position of the matching atoms, taking this parameter, we have distributed all these different structures in these two groups that actually are the two structure types of this family. And you can see that we can quite well distinguish by the maximum distance. Before I continue, I will like to highlight that there are, when we are talking about the comparison of crystal structure, there are many different parameters that can be used in the literature. But there is, I think, a common problem that I don't know if really has a solution, in the sense that there is not a recipe. There is not, I mean, there is not a value that you can say, if you have a value higher than this, that means that the structures are not similar, or if this value is lower than this parameter, if your parameter have this value is less than this, the structure are similar. So there is no such a recipe. At the end, you need to think a little bit more. That's why I think that, for example, in this definition, they use the term, they put that the geometric interrelationship are similar without specifying what similar is, because there is not a general rule. So now let's return to the algorithm behind COMPSTRU for the comparison of a structure, because this method, as other methods, has some limitations, and I would like to discuss them with you. So, as I mentioned earlier, the program generates all equivalent descriptions of a structure true, and it searches for the best match of the lattice parameters using the affine normalizer, and then looks for the best match of the atomic coordinates using the Euclidean normalizer. So the difficulty arises when comparing triclinic and monoclinic structures. So in this case, the affine normalizers are not space groups, and their symmetry operations are expressed in a parametric form. This sometimes prevents the program from carrying out a proper comparison. So let's have a look a little bit this in more detail. So here I'm showing the affine normalizer of, as an example of the monoclinic space group CC, the monoclinic space group number 9. So you can see these are this is the parametric form. So in such cases, the program COMPSTRU calculate the best match between the lattice parameters by varying the parameters within the range -3 to -3. So we have chosen this range because it works quite well, and also because of the speed, because increasing this range makes the program very, very slow, and as the server, you are doing the calculations on fly, it's not possible to at the moment to be able to increase this range. So to perform these calculations, the program uses a brute force method and generates all the possible cases with this range of of parameters. And in general, this works. But what if the parameters of these unicell transformations lie outside this range? So in these cases, the program, unfortunately, is unable to compare the structures. That is what we have in this case. Here we have an example of two monoclinic structures that they look quite different, but they are symmetrically equivalent. So in this case, the program COMPSTRU is not able to relate them. The reason is that the values of the elements of the corresponding unit cell transformation are outside of this range from -3 to 3. So we also have a similar problem in another program of the server that is called structure relations, which calculates the symmetry relationship between group-subgroup related structures. So you know that the study of symmetry relationships between crystal structures make it possible to analyze structural phase transitions, explore symmetry relations in structures, and to construct these Berninghausen trees. The relationship between two group-subgroup related structures is described by a transformation metric column pair, which is not, in many cases, is not straightforward to obtain. So in the server, we have a program called structure relations, which is also available in this structure utility section, that can characterize group-subgroup relations between structures with either the same or different compositions. So as input, the user provides the high and the low symmetry structure descriptions, and in the output, among other things, the program provides these transformation metrics. So as an example here, we can consider these two structures, and if you introduce them in the program, it will provide you the transformation metrics relating them. So just to have an idea how the program works, so the program, if you provide your high and the low symmetry structure, the program first calculates the index of this group-subgroup pair, and it then determines all possible transformation matrices relating both the group and the subgroup for that specific index. Once these possible transformation matrices are obtained, then the high symmetry structure description is formed into the subgroup basis for each of them. And finally, among the equivalent description of each transformed structure, the program searches for the one that best matches the low symmetry structure description. So how does the program do this? It uses part of the method from COMPSTRU, which relies on defining Euclidean normalized of the space groups. So that's why for triclinic and monoclinic structures, this approach might not always succeed in finding the correct relationship. So this limitation in our method is not only affecting one of our programs, COMPSTRU, but also the program structure relation. Now, just to sum up here, I'm showing some conclusions. So the algorithm of the program COMPSTRU can be used to quantify the similarity of two structural models of the same phase or structures with different compositions, which are isopointal, and as a tool for the classification of isopointal structures into isoconfigurational structure types. This method is a pure geometric analysis and needs to be complemented by crystal chemistry or structure chemistry studies to decide whether your structures are similar or not based on the calculations of the program COMPSTRU. Then the method that based in which is in the COMPSTRU space has its limitations, and for triclinic and monoclinic structure, we are a new approach is still required, and we are trying to work on this. So thank you for your attention.
Thank you, Gemma. So please thank Gemma for the presentation. I'll stop recording.